me. Well, come on in, everybody. Make yourself comfortable. I trust that you all are. We're going to give things a few minutes here. Not quite 1 o'clock. We'll give folks a little bit of time to get into the room. Come on in, take a seat, take your hat off. Hope everybody's staying cool. Hey, if you're joining us this afternoon, for this talk on Texas soils and the SoilWeb app, yes, feel free to, please do drop us a comment. Let us know where you're watching from. It's always great to see how far and wide these videos can go, so let us know where you're watching from. And we'll give things just another minute here to get started. Leon County, Lampasas, all right. Fort Bend County, good deal. We're so happy to have you guys today. Keller, Texas. Fort Worth, El Paso, man, we've covered the whole state. Rio Grande Valley, now we've covered almost the whole state. All right. Katy, Fort Bend. Great. Happy you guys are here. Yes, please let us know where you're watching from. We'll get started here in just seconds. Bell County, Lake Fork, all right. Flower Mound, Temple, we'll talk. I mentioned Temple here coming up in the presentation. Well, I hope the audio is coming through for everybody. This is kind of a new experience for all of us in these different times. This will be my first Facebook Live presentation, so I hope it's useful to you folks. I wish you guys could see me. I haven't figured out how to share my screen, share desktop, and have a video webcam of myself at the same time. But if you've been on our page, you saw my face in the video. You can just imagine what I look like sitting in my office in Hallettsville, Texas. Happy to bring you guys some information on soils and the SoilWeb app. So let's go ahead and get started. Thank you all for joining us. As kind of a disclaimer, I just want to say that I am not a soil scientist or a soil specialist. My name is Stephen Yannock. I'm an extension program specialist in the Department of Horticultural Sciences with Texas A&M AgriLife Extension. I have an office in Hallettsville, as I said, and just quickly about me, soils are not even my specialty. My project is working on what we call sustainable fruit project, so I'm intensely studying olives in Texas and a few other fruit species, blackberries, pomegranates, pears, table grapes. So we're doing some different studies on those. So that's what I'm doing. But I have a great personal interest in soils, and I think that's what leads to a great understanding, is having that interest yourself. So let's go ahead and dive in. I'm not going to be able to teach you about soils and all the soil types, folks. We could have an hour-long class every single day for the next 365 days, and I would not be able to teach you everything that there is to know about soils. And in fact, we're learning more and more about soils every single day, and for good reason. This is a nice quote from Paul Harvey that hopefully you've seen around. So it says, "Despite all of our accomplishments, we owe our existence to a 6-inch layer of topsoil and the fact that it rains," which has some truth to it. We know today that our roots can go deeper than 6 inches, and we'll talk about this later on in the presentation. But really, the soil is the foundation of terrestrial life on Earth. Everything starts with the soil. And understanding soil is not simple. Soil is an extremely complex and dynamic body. There are thousands of variations. In fact, in Texas alone, there's about 1,300 soil series in Texas, and even within those series, there is some variation among the individual soil types. And so we recognize each soil type as a unique individual. And that unique individual, just like every one of us humans is unique in some way, we may have some similarities, and soils have similarities in general, but each specific site is unique, and that's because of the way it is formed, and the soil formation is influenced by many things. First, the parent material, or the bedrock, what the soil came from underneath. It's influenced by the local climate. How much does it rain? Does it freeze? Hurricanes, tornadoes, fire, those things. The relief or the slope of that particular landscape. The organisms, both the organisms on top, our macroorganisms that we think of on top of the soil, animals, and also the organisms in the soil have an impact on the soil formation. And then, of course, time. We know that it takes, I think I've heard at one point, it takes about 100 years to form new soil the thickness of a dime. And so this is a precious, precious resource that we have in soils, and it really is a resource worth billions and billions of dollars when we try to sit down and put numbers to it. And so we recognize each soil type as unique, but we didn't always know this. So just a very brief history on the soil survey. Prior to the 1900s, we knew very, very little about soil. There are some records that indicate as far back as 3000 BC that the Chinese were doing some type of soil mapping and trying to classify soils, but they probably didn't get very far and their understanding was limited. The first people trying to study soil in the US and even in Europe and across the world were typically geologists. They had understanding of rocks and the formation of rocks. And so they tried to classify soils based on the types of rocks they found. And that was okay, that led them to some understanding, but that wasn't the full picture. So some of the early investigators were also influenced by their faith. This was interesting information I found looking back at the history. They tried to explain, for example, the glacial deposits in the northeastern US with accounts of the Great Flood, right? The Great Flood and Noah, the story from the Bible. They tried to explain it that way because they either didn't know about the Ice Age and the glaciers, or they were stuck to their faith and that understanding. So that hindered or influenced their understanding. There were also disagreements about how soil should be classified. Is it classified based on the physical properties or the chemical properties, or maybe based on the vegetation that's growing there? And they didn't know how to classify what was the most important classification because there was disagreement about what exactly made a soil productive. Realize 1900s or prior to 1900s, our understanding was very, very minimal. So in 1899, the National Cooperative Soil Survey was initiated. It's a partnership of federal and state agencies led by what was then the Federal Division of Soils. There was many name changes, reorganizations, and it ended up becoming its own bureau in the end. We would know it today as the Soil Conservation Service, which has later, more recently, been renamed as the Natural Resources Conservation Service. And that state cooperation included state experiment stations, including the 10 of them that are in Texas. That first year, their total budget, 1899, was $16,300. And with that budget, they mapped 720,000 acres that first year. It was pretty impressive. But there's this paradigm of the soil. To understand the soil, we need to investigate the soil. And to investigate, we need to be able to classify the soil. And so it's kind of this feedback or this round and round loop where, okay, we need to investigate to understand, but to understand, we need to investigate. And so there was kind of a rocky, slow start. And so if you can imagine, 1899, early 1900s, these folks going out, mostly on horse and buggy, with simple rudimentary tools, trying to collect data and here's a guy looking at the slope of the land with a plane. And so their first category that they used to classify soils was texture. This is the big one that we should all recognize. The texture means the percent of sand, silt, and clay particles in the soil. Then the second category they added was local names. And so an example of that here around me is like a Hallettsville fine sandy loam. And if you familiarize yourself with soil, you start to see how these soil types and series are named after local communities where that soil was originally categorized and classified. By 1901, they identified 100 soil types, and you can see by 1912, 1,650, and that number just continued to grow. By 1911, they added more categories. They realized color was important, drainage, organic matter, oxidation, land capability, erosion. They realized that all these things played a part in the productivity and the classification of soils, and so they added these categories. They even tried to lump groups of soil into these great big provinces, one that expanded from Miami to Montana, saying, well, the vegetation is somewhat similar in this large area. But of course, today we realize there's such great variation from Miami to Montana, so provinces were abandoned quickly. But their accuracy in those early years was terrible, although so was their understanding of soils at that time. For example, they mapped only 2 soil types in 736 square miles in Mississippi at one point, just 2 soil types. And we know that even on 1 acre today, you can have multiple soil types on a small area like 1 acre. And so I go through this not to bore you with history, but to give you an understanding. When we get into looking at soil maps, you might feel overwhelmed by all of the data that's there. And so I wanted to give you this background and maybe help you understand why they have all this data about the soil and where it came from and why it makes sense, why it helps. 1922, they finally laid out a basis for classifying soils like we do with biological organisms. So in biology, hopefully you remember from high school, the domain, kingdom, phylum, and so on. So they did something similar in soils. They classified by order, that's the greatest, largest group, and then everything under that, suborder, great group, and so on. They published this classification system finally in 1975. And they've updated it. There's a new volume that came out in 1999. And I tell you this again to help you realize we are still learning about soil science. This is not a topic that's been studied and put to rest long ago because we know everything about it. We're still learning today. So that comprehensive classification system is called Soil Taxonomy. It's only 886 pages. That's all you need to read to understand how soils are classified and how to interpret soil surveys. And there's still amendments ongoing today on their website. Here was something interesting. Finally, after 111 years, they finished the soil survey in Texas. They had a ceremony in 2010 to symbolize the last acre that was finally finished surveying. They mapped 171 million acres. They collected this monolith that you see in the picture there of Houston black clay, recognized as a state soil of Texas for its importance to the agriculture of the state and the history of the state. And you can see that if you folks that live in that Houston black clay or the black lands of Texas, you see in that monolith the typical cracking that comes along with that Houston clay, that shrink swell clay. So the soil survey and you, what can the soil survey do for you? It can help you determine what plants and crops might be suitable based on the limitations of the soil. It can show you your limitations. It can give you an idea of what amendments might be needed, the potential for erosion, and much, much more. So there's many ways to access this soil survey. One is the original way. Go to your local natural resource conservation office. Every county, or I believe almost every county, should have a local NRCS office, and they should have paper copies of the soil survey for you to look at and can help you interpret the soils on your land. Then you can print the paper copy for yourself. I'm going to go through that, although the paper copy online that you print lacks the maps and tables, and so that's where the local office comes in. And then there's the online versions that came about here in the 2000s. Web Soil Survey from USDA, and later on the SoilWeb Survey, and that's the one that we're going to be talking about. Now these surveys do have some limitations. As great as they are, they draw straight, clear lines on the maps, and those soil type boundary lines are not exact and precise in real life. There's no clear boundaries between soil types in the landscape, so we have to take that into account. There's some mixing along those lines. Soil maps are typically very accurate, but rarely, occasionally, the soil type is not correct. We've encountered this out in the field where it's supposed to be a sandy type soil and it's a heavy, dark, black soil, clay soil, and so something got mixed up. The soil survey does not account for past or recent human impact, and this is the one, well, what I mean by that is perhaps maybe the soil survey says your soil should be a 6 pH. Well, maybe somebody in the past has limed that soil and now the soil pH has changed. And so it doesn't account for those things. And that last bullet point is the one that probably impacts most of you, if you live in a neighborhood, a subdivision that was built up on fill soil or fill dirt, or even if you're not in a subdivision, if your house was just raised up on fill dirt, keep in mind that the soil maps are not taking that into account. So you may go outside your front door, dig in the soil, and it doesn't match what's on the soil map. That may be because of soil that was brought in to build up a pad for your house. So now we'll go to the web. Let me take just a second. Okay, there's the web browser. And folks, we're going to provide you with the links to all these different places that websites we're looking at today, but I'm going to show you how I get there. SoilWeb. I just Google it. Okay, it comes up fairly easy. So SoilWeb. Oh, I got ahead of myself here. I'm going to go back to USDA NRCS. So you just Google NRCS, go to their home web page. Right here in the very middle says Soil Survey. And here's the button where you can start the online web soil survey. And this is a great, complete tool for you to use. However, it's a bit cumbersome and slow to work, even on the fast internet that I have here. So I've already got some pulled up. And again, I'm not going to show you how to use this one. I wanted to show you how to use the other browser. So this is what it looks like once I've drilled in on my house here. Actually, you can see the lines delineating the different soil types and the abbreviations here of the names. And so I'm in this CMB, that's the soil type I have. I can click on CMB, which is a Cheatham loamy sand. I can click on it, and this is what I'm talking about, how it takes a few moments to get there. This is a wonderful website. I think it's slow because they have so much data on here that it just takes a while to process. So you can pull up, here's the description for the Cheatham loamy sand. We'll just look quickly. It gives you precipitation, average temperatures. It's not classified as prime farmland. Here's the typical profile. It's a loamy sand down to 28 inches, and around that 28 inches it turns to a sandy clay loam. Not much slope. There's no restrictive feature like bedrock. Okay, so here's important information to know. It's moderately well drained. We talk about horticultural crops. We want to know how well the soil drains so we know if we'll have root rot issues or other saturation issues. Well, this one has moderately well drained soil. Depth to the water table can be 2 to 4 feet. There's no frequent flooding. Land capability we're going to talk about in a bit. Hydrologic soil group we'll talk about in a bit. I just wanted to show you this on the web soil survey. There's some things that SoilWeb, the other browser we'll talk about in a moment, there's some things it can't do, and that's probably because they wanted the SoilWeb browser to work much faster, and it does that greatly. But here's an example of what web soil survey can do. If you get in there and you play with it, and I can show you how to do this if you want. You can tell it to show you all of the soils and whether they are prime farmland, or if they're kind of mediocre farmland, or if they're not considered prime farmland. So all the green is prime farmland, the blues are kind of mediocre, and the reds are considered not prime farmland. And so this is helpful. I have people come to me all the time saying, well, I want to grow pecans. I want to start a pecan orchard. What kind of property should I be looking for? Well, here's a great resource. Pull up the area that you want to live in, delineate prime farmland soils, and know that, okay, I want to live in Colorado County. I need to be looking here in the northwest side, or along the Colorado River, or over here on the east side, or the north part. That's where you're going to find those prime farmland soils. So I just wanted to show you that. Okay, back to SoilWeb. This is the one I wanted to show you because even myself, as an extension employee, the web soil survey is just a little bit cumbersome to understand and use. And this one, the SoilWeb from UC Davis, in cooperation with NRCS, is just so much more user-friendly. When you bring up the website, I think it drops you here in Davis, California, probably because that's where it was created, UC Davis. So there's the UC Davis campus right there. So this So you have to slowly zoom in and delineate an area of interest and zoom in on that. On SoilWeb, it's like using Google Maps or Google Earth or one of those other, and I'm not promoting or recommending, brands here. I'm just using common names, but it's easy to click and grab and move around. You can scroll on your mouse to zoom in and out quickly, and it gives you the county outlines. And once you get close enough, one more, boom, there's the soil types, and so it comes up very quickly. So without giving away too much of my privacy, here's basically this is where I live. Here's the same thing we were looking at right here. So there's the house, there's the soil types, and so it's the exact same map. They use the same data. This SoilWeb page uses the same data as the NRCS Web Soil Survey, and so it's easy. You click right there, and that soil type, CMB. Well, this is Cheatham loamy sand. Well, that's what we know. And you see these other names below Cheatham, and that's because this soil type is not, again, there's no clear delineation, there's no clear line in the sand, pun intended. There's mixing, so that this soil is influenced also by the Walkley, the Tremona, the Katy, the Mockley formations. So it's not pure Cheatham, it's 90%, and that gives us a good enough information to go with. When you click on that soil type, it shows you a nice picture of what colors and depths of the horizons of the soil. So you can see, is it very consistent all the way down, or is there a layer that restricts water flow or something? So this is interesting. Then you can go through these different classifications. How much organic matter in the soil? Well, my soil is sandy, has less than 1%, and the organic matter goes down as you go deeper. This part right here, I think, is the most useful to almost anybody looking to understand their soil types better. So you click on clay, and here it shows the depth of the soil, of course in centimeters. I think 50 centimeters is about 20 inches, so 40 inches, 60 inches, and it's saying at about 70 centimeters or about 30 inches, the clay content has a sharp rise. It jumps up to 22%. Okay, look at sand. Okay, it's consistent. Boom, there at about that 70 centimeters or 30-inch mark, sand content drops way down. Well, that mirrors the clay content. So we know there's something happening right there. Okay, this one, KSAT. You say, what the heck is KSAT? Well, it's got a little button. You can click it. The little question mark, okay? It says saturated hydraulic conductivity. This is the ease with which pores of a saturated soil transmit water. So in layman's terms, this is how permeable the soil is, how fast water will flow down through the soil. And we don't need to get too worried about what exact numbers. We just need to know for general purposes that, okay, I've got good infiltration of water for the top 30 inches, and then boom, it falls to almost nothing. Okay, now this is a clue that there's something happening at that 30-inch layer to restrict the movement of water. Okay? You can look at pH also. So pH is fairly consistent between 5 and 6. This KF factor, again, you can click and read about it, but it's basically how erodible is the soil, how susceptible to erosion. There's, again, many other factors, conductivity that you can look at. Sodium absorption ratio is important for certain types of plants, and I don't have time to go through all of these and teach about, soil characteristics and qualities. That's going to have to be on your own, or come to me later on, and I'll be happy to sit down with you and explain what I know. So we can move on down, and it gives you some information. So there's soil taxonomy. So this is an alpha sol type soil. Again, I don't have time to explain all this, but you can click on it and get more information. What I want you to notice right here is this family classification. In particular, this word here, plinthoquic. Plinthoquic. So remember that term. It's going to come into play later on. We can move further down, land capability class. So I remember I talked about they started classifying these on the capability of the land. And okay, 3E. What the heck does 3E mean? That means nothing to me. Well, click on the little question mark. It gives you a brief description And for more information, you click on this link to go to the original agriculture handbook that describes these land capability classifications. And so I'm going to go down quickly and show you where the information is, because I know what I'm doing here, but you can go back and read this on your own. So okay, capability classes. Class 1, soils that have few limitations that restrict their use. Class 2, soils have some moderate limitations that restrict their use or require some conservation. So soils in Class 3 have severe limitations, and so on and so forth through Class 8. And I'll go down through Class 8 and now look at the subclasses. Okay, so here it has the information. Subclass E means its hazard, its particular hazard, the one that's most likely to happen is erosion. So subclass W would mean it has excess water, maybe it floods. S would be limitations in the rooting zone and so forth. So you can find out, you don't have to be a soil scientist to use this web page and help you understand the soils in your area. You can look at the ecological site description of your area, and this can tell you what types of plants, what types of native plants and grasses grew historically. If you're looking to restore some of those natives, it'll show you what species and what composition, gives you information on wind erodibility, typical erosion factors. It says runoff is very low. Well, that makes sense. It's a sandy soil, has high permeability. Again, drainage, moderately well drained. That mirrors what the Web Soil Survey told us. Heydrich rating, that's a rating of wetland soil, so it's not a wetland. Hydrologic group B, this is, again, you can click and read. This is an indication of permeability again. And this is another interesting piece of information it gives. Total plant available water in the soil profile, about 24 centimeters. Now, don't get hung up on the number. You don't need to memorize the exact number and use that in calculations. What I want to show you now is comparing some soils. So I'm going to zoom out to some other soils that I'm familiar with and zoom back in. So here's another piece of property that I'm familiar with. So we click here. This is a Tremona fine sand. Okay, so if we look at this one, it is also termed aquic, and it's classified as a 3E. So it's not great, it's somewhat poorly drained, runoff can be high, and it stores about 25 centimeters of water. Now this is the top of a hill, this Tremona where the red X is. If we go down here where the W's are, this is a creek bottom. This is a flat, this is a creek that runs right here. And so this is a creek bottom soil. The Whitesboro, sandy clay loam, occasionally flooded, it's along the creek. And we can look at all these same things. So if we look at clay in this one, there's no big jump. It's a nice, deep soil that's fairly consistent. There's a little change in sand there. pH is consistent all the way down. Look at the capability on this one. It's a 2. So automatically, without having a heck of a lot of knowledge, I know that this Whitesboro soil along the creek is going to be inherently more fertile and have less limitations for growing crops than, say, this Tremona soil on top of the hill. I did a little digging because I was interested while I was waiting for this to start. I wanted to find a soil that had no limitations. It was land capability classified as a 1. And I found one here. So this is the Colorado River, just outside of Colorado County. And this is farmland, row crop farmland on the river. And if we click on it, it's a Bergstrom silt loam, rarely flooded. And look at this, there's good continuity of depth of soil. pH is nice and consistent all the way down. And here's that land capability class. It's a 1 with no subclass. That means this is beautiful prime farmland or natural habitat, depending on your use. It does not say that term aquic. Okay, so that's the SoilWeb Browser. I'm going to go quickly back to the presentation here. This is back at my house now. So I have sometimes a perched water table in my soil, and I'm going to show you why. I had a video, but we're not going to show a video because it doesn't come through very well. This is my soil. I dug a soil pit in my garden just for this presentation, so you're welcome. It was hot, but it was a lot of fun. I really enjoyed it. So here's the top of the soil. I know I kind of cut that off, but there's the top. I wonder if I can, there we go. And so you see this profile visually mimics what we saw on the SoilWeb browser. That brown color towards the top here, more of a yellow color in the middle, a little bit lighter down below that, lighter horizon, and then they actually had gray here at the bottom. We'll talk about that. Look at where the roots are. This line here, where my finger line is there, is 12 inches. And the majority of roots, here's a 2-foot line. I should have had my tape measure in there. The majority of roots, see there's roots, here's roots, there's a root there, there. The majority of roots are in that top 24 inches. Why? Well, they need oxygen. Roots have to have oxygen to survive. So we know that there's oxygen diffusion this far down in the soil because of the roots, but we also know, if we zoom in here, you see these brown, kind of rusty, orange looking spots? Well, that essentially is rust or similar. This is iron in the soil that has been oxidized. This is iron oxide. So when iron is exposed to oxygen in the soil and is wet and then exposed to oxygen, it oxidizes and turns this rusty red-orange color. So we see evidence of that. Even the overall yellow-orange color of the soil profile indicates that there is oxygen flow through the soil. If this was gray or blue, that would indicate that there is no oxygen or very, very little oxygen in the soil. As we look further down at the profile, you would think, well, you know, beyond 2 feet, there's the 2-foot mark. Beyond that, there's probably not going to be a lot of roots. Well, zoom in. There's roots, there's roots, there's roots, there's roots. And I'm not saying I'm doing anything special at home. These are just probably tree roots from outside the garden. Now this is the interesting part. This subsoil is an interesting part of my soil. Now a lot of you folks around the state are going to have vastly different soils. But those of you in the post oak savanna or what we call the clay pan prairie, you're going to have similar soils to this. So what are we looking at? Okay, well we recognize the red, right? Those are those accumulations of iron oxide. So look, down to 3 feet in the soil. But what's the gray lines? What's causing that? Well, that is a sign of iron reduction. So when iron is trapped in saturated water or saturated soil, and it creates anaerobic conditions, that means there's no oxygen in that water in the soil, iron is reduced. So that's the opposite of oxidation. So when iron is reduced, it turns this gray or blue color. So why the lines? Probably old roots came and penetrated this soil at one point when it was not saturated. That root died and left a small, tiny channel or pore. Well, water flows down that channel or pore, and so water tends to stay more along that channel or pore, and so it tends to stay more saturated along that channel or pore. And so that's why we have this great, beautiful modeling of red and grays in the soil so we do have evidence of saturation because of the reduced iron here, but we also have evidence of oxygenation, of oxidation of the iron. So roots can grow in this, but it can also hold water for periods of time. So you remember that picture of my perched water table? Well, this is why. This is that 30-inch mark that we saw on the SoilWeb browser. Remember where sand percentage was going down to 30 inches and dropped off? And then clay percentage went down to 30 inches and bumped up. This is that reason right there. Remember that also that term aquic? Soils termed with that piece of a word, aquic, those soils are susceptible to having a perched water table or saturated root zone at some point during the growing season that might restrict or limit plant growth. And so in fact that's what happens here. That's what happened to me. I was trying to dig post holes to build figure out what I'm doing here. I was trying to dig post holes to build a trellis for some blackberries. I got down to 24 inches and my hole collapsed and filled up with water. Well, that's because we had a couple inches of rain in the days before and I had water perched on top of that that clay, heavier clay subsoil that's red and gray modeled beneath. And so to kind of wrap things up here, you know, the soil surveys are great. These are wonderful, wonderful tools to help you investigate soils and look and plan. But they're not the be-all, end-all to investigating soil. And so once you've looked at these surveys and gotten some information from them, you have to go back out and do some practical in-person soil investigation. So one of the main things is to check drainage. We always recommend you dig this hole 32 inches deep, 8 inches wide, fill it with water, and don't do it when we're in a drought, and don't do it when we're right after a flood. Do it when the soil is kind of an average moisture. You fill that hole, and if it drains within 8 hours, you have excellent drainage. If it drains within 12 hours, your drainage is decent. But beyond 24 hours, if it takes more than 24 hours to drain that hole, that's a sign that your soil drainage, internal drainage, is maybe limiting to growth of certain types of plants. What other practical ways are there to investigate soil? Well, you can guess and estimate the texture of the soil by feeling. You can estimate soil moisture by feel. I think a lot of folks at home have an issue with estimating soil moisture. Do I need to water? Do I not need to water? How much moisture is in the soil? Where there's guidelines for that, and I'm going to show you those here just briefly. I can find, there we are.